Okay, the opponent team, you have 1 minute to choose the problem to challenge.
We're going to challenge the reporter problem number 2, also any speed.
Okay, number 2. Okay. No, the reporter have 5 minutes to prepare.
Good afternoon, everyone. I'm Rosaline from PF3. The experimental topic I'm going to report is oscillating sphere. And we have 8 parts in our compass. This is our problem statement. A light sphere with a conducting surface is suspended from the thin wire. When the sphere is rotated about its vertical axis thereby twisting the wire and then released, it started to oscillate. Investigate how the presence of a magnetic field affects the motion. So our main focus is how the different distance between sphere and magnetic would affect the motion. This is our video about the experimental device. Our purpose is in this experiment, various related physical quantities can be analyzed through the data. Take the oscillating sphere as the subject of the experiment and then use scatter chart to present the influence of mass and magnetic field on the oscillating sphere. And then we learn how to use the LabVIEW program to present the curves instantly and use Excel to analyze data. And this is our device. Encoder plastic, transparencies, and strong magnetic, mapping, breadboard, Arduino, clay, rubber band, aluminum foil, dugong line, and photogate. I want to mention the encoder in particular. Encoder, since the experiment is to exploit the large angle rotation of the ball, it is necessary to accurately measure the change of theta with time. Moreover, the problem of judging the positive and negative of the orbiting direction and the angle accumulation judgment when it exceeds one circle and it also means q pi must be overcome. Therefore, we use encoder to solve this problem. So, when encoder through photogates. Photogates would accept angle change and send a message to Arduino evaluation board. And this is the wire clamp. Its function is fixed and adjust easily, and the dugong line is to connect the Arduino evaluation board, and encoder, this is encoder tunable. And filters is to place a filter over the bottom of the photogate to attenuate the infrared of the photogate. The dark areas of the encoder could be dark enough, and this is two of photogates. The left side is our formula. And the big letter I is moment of inertia. And the kappa is torque constant, and A is amplitude, and beta is resistance coefficient. And the phi is initial phase, and the last one is rotating angle, angular acceleration. It also means omega, and the angular velocity. So, the first design is control variable, and we use the gentleman length, and we use the 10.5 centimeters rubber band, and the sphere we all use table tennis. And independent variable, we use the mass. We use the clay and the mass on both sides of the sphere. And a dependent variable is we can get a mass rotating sphere scatter chart. The x-axis is time, and also is time and is seconds, and the y-axis is radian, a kind of unit, and the radian of the oscillating sphere decays over time and then stops at 0. And this is more looser than other scatter charts because the time, the radial becomes 0 is stopped at about 60 seconds, and 0.06 gram is like 150 seconds, and a 6.12 gram is like 170 seconds. And this is our amplitude scatter. When the oscillation reaches the maximum value of the section, the difference from the balance point is amplitude. And the axis is time, second 2, and the amplitude is red. And we can get the trend line equation, and we will tidy up later. And this is our period. And you can see the 2.56 gram is about 4 and 5 period. And the 5.06 gram is about 5 to 7. And the 6.12 gram is about 6 to 9. So we can know the bigger the mass, the bigger the period. This is the formula about the amplitude. So we can get a trend line equation, and we can tidy up like beta divided by 2 times inertia and the second design, the control variable is also the pendulum length, and we also use the 10.5 centimeters, and the sphere we put the aluminum foil. And the independent variable is distance between sphere and magnet. And the dependent variable is the different magnet distance with rotating sphere scatter chart. So this is the different distance with the magnet and the radial scatter. The x-axis is time second and the y-axis is radian. So I designed the 2.5 centimeters, 3.2 centimeters, and 4.2 centimeters. And 5.5 centimeters and 6.2 centimeters. And this is the amplitude. The x-axis is time second, and the amplitude and the y-axis is amplitude. centimeter and 6.2 centimeters. And we can get the trend line equation. And this is our period. X-axis is also time second, and the y-axis is also period. And we can see the period is about 4. And 3.2 centimeters is about a little bit go up and a little bit go down. And 4.2 centimeters is also a little bit go up and go down. The 5.5 centimeters is, but the 6.2 centimeters is go down to 3 period. So we also use the formula about the amplitude, and we tidy up the beta divided to design interior. And this is our final average period. So the summary is the bigger the mass, the bigger the period, and the longer the distance of the magnet, and smaller the period. And the mass go up, beta divided by 2 times inertia go down. And the beta divided by 2, inertia go up and then go down when the distance of magnet go longer. Thanks for listening.
Okay, the opponent, you have 2 minutes to raise questions.
And about my first question, I want to ask, do you think the period will be the same?
Sorry?
Do using a period will be the same. The period
You
of
mean a different scatter chart? Or
the period of the sphere rotating
yes?
will be the same.
Almost the same.
Almost the same. And I want to ask, do you think the sphere will stop?
Sphere will stop?
Yes. Do you think the rotation of the sphere will stop?
Channels? Yes.
Yes. And but why? Why do you think the rotation will stop?
Because the pin is here and it will stop at the end after rotating.
Okay. And I want to ask, what is the material of this sphere?
Of this
Sphere. The material of this sphere.
tennis pin, table tennis.
Table tennis.
Yes.
In the problem statement, it says you need to use the conducting surface. So in a
Yes, we don't use the aluminum foil in this video. We don't use the aluminum foil in this video.
okay. Time's up. Thank you.
The opponent has 3 minutes to prepare. Okay, the opponent that you have is most 2 minutes for your speech.
Honorable honorable juries and the fellow competitors, and the opponent from the team, the physicists teams. And the problem statement, we can see the reporter focus on investigate how the presence of the magnetic field affect the motion. And their main focus is what the effect of the distance between the sphere and the magnet. And this is the structure of the report. The first is about the problem statement. She said about the distance of the magnet and the sphere. But we didn't see the theoretical model. And about setup, we can see in the setup they use the tennis ball as the sphere. And about the experimentation, we can see their parameter is about the distance and the mass of their sphere. And about the conclusion, let's say when the mass of the sphere is bigger and the period of the sphere rotation will be bigger. And I want to talk about the strong and weak point of the reporter. The first is a strong point. She has good delivery and frequency, and fine experimental data. But the weak point is lack of the theory of the magnetic field. And the second is why she used table tennis and with no obvious reason. And the third is no error bars added in she's data. And the points to be discussed. The first is about the observation. I want to talk about the rotation. And the experimental setup, I want to ask about the table tennis and the magnet. The magnetic field made by this magnet. And the theory, I want to talk about the decay period of the rotation of the sphere. And let's get into a discussion point. Continue the question I just asked you. You think that the sphere will stop because I think that the rotation of the sphere will stop too, because there is energy loss in the sphere rotation. But we can see that you use the tennis ball, but the problem statement is the conducting surface. So I think this may cause you didn't consider the charge density of the sphere, and the charge density may be a damping of the rotation. And you use a magnet to provide the magnetic field, is it?
Yes.
And do you measure the magnetic field of the magnet?
No.
No? In opponent's viewpoint, we think that you should measure the magnetic field strength of the magnet, because the magnetic field strength of the magnet is not balanced. And second, do you consist the wire friction affect the rotation of this ball?
You mean the rubber band?
Yes.
No.
No? In opponent's view, we think that the friction between the wire and this ball will cause the rotation decay. And continue to the question I just asked you. Do you think the period will be the same? That you say almost same. But I think if you use the conducting sphere, that it will have magnetic damping. And do you consider air resistance of the rotation?
Should I consider
Air resistance
air resistance?
when the sphere starts rotating?
Maybe yes.
Maybe yes. And do you And in my opinion, I think the period of the sphere rotation will decay because of the magnetic damping and the friction between the wire and the sphere, and the air resistance between the air and the sphere. Could you turn to page 7? And we can see this data is about the force and the time. And I want to ask, how do you measure the force in this data?
Force in this data.
Yes,
This one.
this one. How do you measure the force?
This one to this one. Yes.
Yes.
Also, I minus the lowest amplitude. Our amplitude minus the lowest amplitude.
Okay. And in this data, we can see the force decays over time. Could you explain why?
Sorry.
Could you explain why the force decays over time?
Play over time.
In
Because
this data, you can see the force
yeah,
from 10 Newton to 0 Newton. Could you explain?
because the amplitude will be declared, so this charge will be almost get to the 0.
Okay. And continue to the question I just asked. And you see you use a magnet to make a magnetic field. But in my opinion, I think she could use the Helmholtz coil to provide a balanced magnetic field to the x-axis. And I want to ask, do you make a coordinate system of the sphere?
I'm sorry, but this one is kind of mainly scatter chart that I want to put. I just example here.
Just a simple.
So the most important is the radiant and amplitude and measure the scatter chart.
Okay. And do you consider the rotation angle decay in your experiment?
In my experiment,
Yes. Do you think the angle of the sphere rotation decay? The amplitude becomes smaller. Do you
Yes.
think? But when I asked you, you just asked that you think the period will be the same. So I think the period of the rotation will decay over time. And could you turn to the page 8?
8.
Next. Could you turn to the page there about theory? About your theory. That is tau and minus property. Theory. Oh, let it. Okay, could you turn to page 20? Yes, and in this equation, do you think the decay will be exponential?
Can we repeat exponentially?
Yeah, exponentially. I think in this equation it is exponentially because you have the e and because of these, because of the exponentially
Yes.
decay.
Okay.
And I want to talk about your first experiment.
You say the aluminum.
The mass of the
aluminum
sphere.
foil.
No, the mass of the sphere.
Yes. This one?
The first experiment, your first independent variables. and you consider the mass on both sides of the sphere.
Yes.
Yes, but in the problem statement, it talks about a light mass in but conducting sphere.
This is just a refer to the most important is the aluminum foil with the tennis ball.
With the tennis ball.
Yes, this is just a reference.
Okay, the reference.
Yes.
And next discussion about the conducting surface. If your sphere is conducting, that you can imagine. I think that you can imagine the sphere is consists of so many coils like this. The sphere is consists of so many coils, and when the magnetic field gets to a coil and you give the initial rotation to this sphere, and because the variation of the magnetic flux, so by length law, and it could create by length law, it could create a current to this direction, and then by right hand rule, the magnetic field direction is upward, and the current is forward, and the current is upward. Then make a direction, make a force to this here, and here is the direction of the sphere rotating. So I think this makes us the magnetic damping of the sphere. So I just feel weird why you use the tennis ball instead of aluminum ball or stainless ball.
We use the tennis ball, and outside we cover the aluminum foil.
Yes, maybe
Yes.
you can use aluminum cover this ball, and maybe you can use the stainless to make this sphere. In my opinion.
Okay.
And I think, do you consider the angular velocity of the sphere rotation?
No.
And do you think the angular rotation decay? The decay of the angle, the rotation.
Yes.
And my discussion part is to here.
Okay, the opponent, please summarize the discussion.
And in the discussion, I discussed the experiment setup of the conducting sphere and the not conducting sphere about the magnetic field damping. And we talk about the magnet, the non-balanced magnetic field and balanced magnetic field. And in the observation video, we discussed about the rotation and the angular velocity of the sphere. And in the theory, we discussed about the decay period is exponentially. Yes, and this is my summary of the discussion.
Okay. The reviewer, please ask questions in 3 minutes.
Okay, so I want to ask the reporter, why you choose the distance and mass as variable?
Why?
Yeah.
Why did I choose?
Okay, never mind. Okay, and I want to ask the opponent, how will the friction affect the experiment result?
What is the friction?
How will the friction affect the experiment as well?
The friction is the friction between the wire and the sphere. Yes. I think the friction will affect the rotation.
Okay. And how will you advise reporter to promote the experimental device?
I think she could replace her pencil to the conducting sphere, like the aluminum material or the stainless material. And she could change her magnet to the Helmholtz coil that provide balanced magnetic field.
Okay, thank you. And can you turn to page 28? And I want to ask about the second chart. Can you explain the inclination and declination of the chart?
You mean the inflection of this chart?
Yeah.
So I got this scatter chart from the amplitude scatter chart. I catch the amplitude and made this pivot.
Can you explain why? Why? What's the number? Never mind. And I want to ask both of you why the amplitude and period is important in the experiment.
Pardon? About the amplitude
And period.
amplitude and the period.
Yes.
I think because I just mentioned the amplitude is about the rotation of the sphere, while decay because of the magnetic damping air resistance and the friction between the wire and the sphere.
So I think we can get a period, so we can find out the theory for the period scatter chart.
Okay. Thank you.
Okay, the review I have 2 minutes to prepare.它在项目。Okay, the review take the floor.
Okay, so from our family and from Golden Girls Senior High School. And the purpose statement is a light sphere with a conducting surface is suspended from a thin wire. When the sphere is rotated about its vertical axis, you might just see the wire. and then release, it starts to oscillate. Investigate how the presence of a magnetic field affects the motion. And the main focus are how the different distance between sphere and magnet could affect the motion. Several variables. Pendulum depth, 10.5 centimeters sphere table tennis. And the overview of the reporter. For the pros, have a clear view of experiment setup and done a great job at experiment. Have adequate data to explain the phenomenon. For the cons, didn't explain inclination and declinations of the chart. Didn't put the setup photo well. The table tennis and metal foil. Didn't include the theoretical model. Didn't measure the magnetic field. Didn't consider other factors. And the overview of the opponent. For the pros, consider the material of the sphere. Have a clear view on the reporter's structure and consider different variables. For the cons, didn't talk about the process of the experiment. And the discuss about the period will be the same or not. For the reporter, they think yes, think the rotation will eventually stop. And for the opponent, they think no, think the rotation will decay because of the air system and the magnetic system. And for reviewer, we agree with the opponent. Can be proved by reporter's chart. And the missing point, for the reporter, they didn't talk about the process of the experiment and didn't consider their parameters. And for the opponent, they didn't talk about the process of the experiment. And questions of the reviewer to the reporter and the opponent and answers to the questions. Why the amplitude is important? For the reporter, the period and the amplitude can prove the theory. And for the opponent, rotation of the sphere. And thank you.
Okay, the reporter, you have 2 minutes to make your concluding remarks.
So I think I don't set up the right photo with where of the friction, and I don't explain period phenomenon and the process of the experiment. And opponent asked me where the sphere stuff. I said yes, and what's the material of my sphere? I said the table tennis, and is the period the same? I said very close. And do I consider air resistance when the air starts rotating? And I say yes. And how do I measure the force? I say our amplitude minus the lowest amplitude. And in the first experiment, the mass of the sphere, and I consider the angular velocity. I say no, and I didn't explain the phenomenon. Thank you.
Okay. Questions from the students?
Okay, we'll kind of, I'm curious about the problem set up is the light sphere, but it's a conducting sphere, conducting surface. And so you said in the picture, in the photo you show there's no aluminum foil on it, but in the experiment you have that, right?
Yes.
So, but your magnet is put on the bottom, right? The magnet.
Yes.
And
Backpack?
the magnet.
No.
Where you put the magnet? I'm sorry, I didn't see very clearly.
Here?
Oh, okay. That picture, that photo has the aluminum foil and also the magnet. From one side only, or both sides.
One side.
Magnet
One
on
side.
one side only.
Yes.
Okay. And that's the only setup with the magnetic field, right? That's the only setup.
Yes.
Okay, so you don't pick the other setup to set up. Maybe you have different magnetic fields to see the effects on the sphere. So I think the data actually is kind of not enough to see all the change. I think, yeah, maybe if you have next time you're gonna do the experiment, you're gonna try more about the different magnetic setup, like the opponent's suggestion about how to make, especially if we can control the magnetic field, like the Hanko's coil, you know, we change the current to adjust the magnetic field. So that would be easier to see the difference.
Yes.
I'm sorry. This is not a question. Okay, so how about you? So how are you gonna do the experiment in your?
If it's me, I will use Hanko's coil to provide a balanced magnetic field to the sphere, and I will use a conducting material of the sphere, and I can use the power supply to adjust the magnetic field strength to the sphere.
So you mean sphere is like aluminum sphere or stainless steels? Is that what you mean?
I think
Metal sphere. No.
just conducting material can do this experiment.
Okay. All right. How about
Okay. For the sphere, it's rotating this way, right? And the rotor have the magnet on the side, right? It's rotating this way, and the magnet is on the side. And if you do experiment where you put the magnet, I mean, the oscillation is in this direction. Magnetic field is in this direction. And do you think the direction matter? The field direction, the magnetic field direction.
The direction of the magnetic
Yeah,
field.
the direction of the magnetic
If
field.
it's me, I will put
With respect to the rotation, because the rotation is in this way, right?
the rotation is twisting.
the sphere?
Yeah, the
the
sphere is
twisting.
rotating this way, so, okay, the angular momentum is this side.
Yes.
Okay, it's up. Okay.
And if it's me, I will use two magnets that one at here and one at there to make a more balanced magnetic field. And then we can use the right-hand rule that we can calculate the magnetic field and
Okay. And how about the reviewer?
And I will use the light conducting sphere and control the magnetic field, just like the opponent just said.
Okay, let's go in time. For the reporter, five, 4, 5, 5, 5.
5, 4, 5, 5. 改错，我等下再改。
For the opponent, 6, 8, 6, 7, 6.
6, 8, 6, 7, 6.
Let's hold
6, 6.
No, 8.
6, 8, 6, 7, 6. Okay.
For the reviewer, 6, 6, 6, 6, 6. No error bar.
No error bar.
Okay, let's finish the stage 1.
Categories.
Which one?
Quick one.
There.
We will send the challenge.
Okay. No, the reporter have 5 minutes to prepare. Please write the name of your representative.
juries and fellow competitors, I'm the reporter from the PF3 High School, and I'm going to talk about the problem of rice kettlebell. And here's our problem statement. Take a vessel and pour some granular material into it. For example, the rice. If you dip spoon into it, then at a certain depth of immersion, you can lift the vessel and contents by holding the spoon. Explain this phenomenon and explore the relevant parameter of the system. And here's our main focus. The first is explain why the vessel will be lifted. And the second is the significance of granular material. And the third is the relevant parameters about the diameter and the grain size. And here's our outline. The first, I will talk about the observation, about the qualitative explanation. And the second is our theory about packing fractions and the viscoelasticity. And the third is the experimentation about the depth of the rod and the average grain size and the diameter of the vessel. And the last is the conclusion. And here's our experimental setup. First, we use the force gauge to measure the pulling force, and the rod we use, and the diameter of it is 2.65 centimeters. And the wooden stand. With this wooden stand, we make the experiment more repeatedly. And with this stand, we can do this experiment without touch the vessel by our hand. And about the stuffed grain, we use two kinds of granular material. The one is flexible, and the diameter of them is 1 millimeter, and the second is the rice. And the vessel we use is the 3D printing vessel. And we shape the vessel to control the same packing fraction. V equals to 0.638. And here's our qualitative explanation. And applied force causes the particles of the granular material to rearrange themselves into the more ordered crystalline structure. And when the rod is being pulled, the contact plane of rod and granular layer is densely packed together and causing the upward force, which lifts up the vessel. And here's about our theory. Our theory first is about the packing friction, and the second is the viscoelasticity of granular objects. And the third, we establish a DEM model and empirical line. And here, we can see the diagram of the tail to the feet. And when the feet is bigger than Vj, the granular material in the vessel is jammed. So in this condition, you can lift up the vessel with the spoon. And when the V is smaller than Vs, the condition of the granular material in the vessel is unjammed. So in this condition, you can't pull the vessel. And we can see between the Vj and the Vs, there is two different conditions. The first condition is this green part. This green part is called the jam state. And we can see this red part called the fragile state. And when we increasing packing fraction and stress, will induce jamming and positive pressure. And we define V equals to total volume of grain over the confining volume. And there's the interesting equation about the shear modulus and the bulk modulus. The increasing of stress and packing fraction will cause the jamming of the granular material. And here, we are going to talk about viscoelastic properties of the packing. And the packing fraction, V, is being used to describe the magnitude for the packing. And you can see the diagram here. In the first part, we can see the granular particles form so many force chains, and these force chains connect these particles together. And at the second part, we can see the force chain break, and so the granular particles start a little bit sliding. And in the third part, we can see the particle form the jam condition. And the condition of the granular material here is cross-tactic. And we have the expression about this phenomenon. And the sigma means the stress, and the G means the relaxation modulus, and the gamma means the strength. And the jamming occurs when packing fraction is higher than the threshold. You can see here when your pulling force is lower than this line, and you can pull the vessel up. But on the contrary, when your pulling force is higher than this line, and you can't pull these vessels up. And after viewing so many literature about the granular material properties, and we can't establish an exact model about this phenomenon, but we see that many of them use this discrete element method, that the sigma means the stress tensor, and the Rij means the contact vector from one particle to another. And the Fij means the force vector, and this is the outer products. The V means the volume of the system. And let's talk about the force on the stick. We can use this empirical equation to evidence this phenomenon. The μs means the rod coating dependent friction, and the P means the parameter of the rod, and the gamma means the specific weight of the grain, and the H means the depth of the rod in this vessel. And let's talk about our experimentation. And first, I would like to talk about the depth of the rod. And the second is the average radius of the granular object. And the third is the diameter of the vessel. Here is the parameter for the depth of the rod. And by this empirical equation, we can get the linear relationship as expected from the empirical equation. And we do 50 experiments as each data. And the error bar enlarged because the granular particle is so hard to control their initial station. So the error bar here will be bigger than the normal experimentation. And about the depth of the rod, the packing fraction be at the bottom of the vessel due to pressure of the above grain. Therefore, we have to exert more force to withdraw the force. And you can see the density of the granular material is higher than the material here. So when we stick the rod into the vessel, we need to use more force to pull the vessels up. And let's talk about the average radius of the grain. And also by this equation, we can get the mixing of the similar grain will cause bigger contact area with the rock and causing a bigger force. And here is the diagram about the force to the mixes rate. And we can get that is about a inversely proportional linear relationship. And let's talk about diameter of the vessel. This is a diagram about force to the diameter. And we can see we get the exponential proportional, and the diameter of the vessel will affect the contact plane of the grain layer and the wall of the vessel. And the experiment data perfectly correlate with diameter cube. And the explanation for the cubic fitting. The area equation is pi r squared h, and the distance for a stretch to reach the vessel of the wall, and is proportional to the r. And therefore, the force will be proportional to r. And we can see when the radius is farther than the center, and it becomes some strain condition to the force chain. And this is my presentation. Thanks for listening.
Okay, the opponent please expectations include.
So please, will show the page of the depth of the rod.
Yeah.
So,
Previous one.
previous one. Like, so is this empty or full of things alive?
About this part.
Yes.
This part is a sharp point of the rock. So this space is stuffed by the rock, not for the granular material.
So your stick isn't in a stable, like the surface isn't stable, right? So do you think this will affect the friction between the form? Like
The
if
surface.
the stick is like this,
Yes.
but your stick is like this, do you think these two sides will affect the result?
You mean without this space?
Yes.
I think because the sharp point won't affect this experiment larger. I think just a small effect.
And the next question is, do you think the diameter of that, so this factor, the phenomenon will change, move to the diameter of vessel? Here. Do you think that this point will turn to here because it is more stable?
You say the point moved to here?
Yeah.
No, I don't think so, because you can see it is exponentially. The line is exponentially. So the dot to the further will be stable to the line. Not.
So are you saying that the depth of the things will not affect?
Time is up.
Thank you.
The preparation for the opponent is 3 minutes.
颗粒的个头，全部写这么长。构成，其实我们要看看这个是吧？因为我在想说，这些都是我们希望和往后的大小，这个无论是多少的话，都是像这个水方面，做这样的一个直径的一种小，是说多少分吧？放上去3点多，7点多，直径的多少？我也在那个小多少，就装过去。我就说你这个真的要这个60多点多点，这样怎么弄？那个都是很粗的。还有那个容器大小，放心怎么和长时间的规定，然后这个跟实际力量也不一样，重量也不一样，这样动是越多越重，对，打不起来。
Okay, the opponent, please take a blower. You have at most 4 minutes.
So we discussed about the depth of the rod, and so he said that the stick, the surface, there is a thicker point of here, and it wouldn't affect the friction it can afford. But I disagree with it because when the friction is caused by how it breaks down when pulling to a stick. So if you break down the rice in a smaller motion, it can afford more friction. And then we discussed about the diameters of vessel would change after in a certain point. But I think this might change because in my experiment I also did about this, and it has a turning point. So I think for advice, he should set more data. This device only 2 for forming a straight line. And then I also think that the charge and the reporter isn't drawn correctly because some of the point isn't close of the average. And then I also saw one of the chart. The line didn't touch any of the average point. And then, okay, so, and I also want to discuss further to the reporter. So, by shaking vessel can conclude the same coefficient.
Shaking the vessel to make the sentence question.
Yes. In your prediction, I remember it's like 5 weeks.
You think about the setup?
Yes, because you said you shape the vessel and this can be the same coefficient, right? Here. So why?
We shape the vessel is to contract the same packing fraction. And the packing fraction that just I mentioned is mean the granular material volume in the vessel volume.
So, do you agree that the velocity of rice pouring into the tube affects the result?
Say the velocity.
When you pour the rice into the tube.
The velocity when I pour the rice into a tube.
Yeah.
But I think the final result is you use the granular material to stuff the space in the vessel. So I think the pouring velocity won't affect the experimental vessel much.
So I disagree with it because the pouring velocity will affect the attachment of the rice with the stick, which means its density may be changed. And the density is very important because the friction is related to the attachment between the stick and the.
Right.
Yes, right. Okay, so then do you agree that the speed of pulling the stick will affect the result?
You say the speed when you pull a rod, I think it will affect.
I agree with you. And so, do you think different angle of inserting the stick will also affect the result?
Different angle when you
Like,
stick the rod into.
Yes.
I didn't do the research about the different angle because in our theory is just vertical stick into the vessel. So maybe we can do the research about the different angle.
Okay, so what do you think about the structure of this phenomenon? Like, is it like a fluid or rigid body more?
You say the fluid and rigid is about the granular material in the vessel.
Yes, when the phenomenon occurs.
When the phenomenon occurs, just I mentioned that we have three parts of the phenomenon, and when in the last part, just when you pull the rod, that it is the jam condition, so it's more likely to the rigid condition.
Okay, so do you measure from which depth the stick couldn't afford the mass of the rod?
You say the boundary condition of the depth.
Yes, I think it's in the depth, about the depth. Here, so do you know which part it cannot afford it at all? Like, it cannot pull the rod off.
No, I didn't do the research about the boundary condition.
It's okay. So here I want to ask, why did you choose this linear line instead of just choosing the maximum friction, the maximum point? Because the main thing you are discussing is about the maximum friction the stick and the rod stick can afford. So why did you choose like a linear point instead of just the maximum point or just comparing the average point?
You say the maximum value.
Yes.
But you say about this part.
Right.
Yeah. But this is the error in our experiment. So I think you can't use this the maximum data. Not just the one data. You can use this data to prove the phenomenon.
I agree with you, good. Also, I want to ask, do you think that the line is actually like this and the line? It is not a linear line, right? I mean, if you compare the average point.
Compare the average of the
blue point.
blue point.
Yes.
And we do the relevant line to this spot. So when we do this search, it becomes like this.
Okay, so maybe in my opinion, I think you should just I think the line is not like it doesn't have like this slope really obviously. I think it shouldn't connect with.
So in your opinion, you think that I should connect these blue stars together, and we can get a line like this, and here to here.
I mean, maybe I could go like this. Right.
A little.
I think this is more better than just pointing like this because some of the, like here, the point is obviously not really close to the average, right?
Just say about here.
Yeah, right.
And just what I mentioned, when the depth of the rod is deeper than the pulling force that you pull the vessel should be bigger also. So I think the blue dot above the linear line is because of this of this phenomenon. So,
Which phenomenon?
do you the phenomenon about force?
So, what kind of material is your vessel?
What kind of the material is the vessel? Just I mentioned, the vessel is 3D printing, so the material of this is plastic.
So, do you think different material affects the maximum friction?
Like you mentioned that maybe we can change the vessel to different material and change the friction between the wall of the vessel and between the granular material.
Right. So, because the only thing of the force is between rise and the stick, right?
Yes.
So, if we change the tube, but the tube has the force with the rise didn't connect with the stick, right?
Yes.
So, did you think that the material of the tube will affect the friction?
Yes, I think the material will affect friction.
Oh, I agree. And then, so how do you know that the data you collect is the static friction instead of the kinetic friction?
About the static friction of the granular material. About this data, or which data?
Like all the data.
All the data.
Right. So how did you make sure it is actually the static friction instead of other things?
You say the kinetic friction and the static friction.
Right.
And three different conditions. Just like I mentioned, when in this condition, I said that there is a little bit sliding. So I think the friction will change a little bit in this condition.
This is the I'm actually asking the data you collect. How do you make sure it is actually static friction instead of kinetic friction?
I didn't mention that my data is static friction. That's because of these three conditions.
But the chart you made is actually said it is friction, right? And you also have the formula about static friction, and you didn't put kinetic friction formula on it. So I assume you think that this phenomenon is caused by static friction, but you didn't tell us why. How did you make sure the phenomenon is actually static friction instead of kinetic friction?
Okay, so you suggest that we can put a formula about the kinetic friction and we can do the comparison.
Actually, I just want you to make sure the data you collect is true for this theory, right? And so another question I want to ask is, how do you know the accurate attachment of the specific area of the stick?
They say about these attachments.
Right.
Just make sure the attachment to stable or
Because sometimes the stick, here's the stick, and the rice, sometimes the rice will be like this. It's very dense, right? But sometimes it will be like this. Right. So here, there's no attachment between the rice and the stick. You agree?
just I mentioned, this is hard for us to control the initial arrangement of the granular material.
Right. So can you measure the attachment of the stick and the rice for the whole system?
No, I think can. Because we can establish accurate theoretical model of this.
Well, I disagree with you because you have already calculated the the reg and the stick reg. So it will be like this. Here is F, and here is F, and here's M. And so if you know F, and you also know MG, and you also know the coefficient, you'll know the whole attachment of the system.
Say, and what does this F mean?
The force you call.
The force you call, but I think the F here should.
Okay, time is up. The opponent, please summarize the discussion.
So in our discussion, we talk about how do they know the correct attachment of specific area of the stick. I think he didn't answer this question really fairly, and then they also cannot conclude whether their data is actually the maximum static friction. And I also discussed about what kind of material is the vessel will affect. So I agree with the reporter because I do think that the material of the vessel will affect the friction it can afford because rise is connected to the stick and the stick is vessel is connected to the rise and the rise is connected to the stick. So the force between each other will have opposite sides of force. So I think it will affect. And so another question is why
Okay, time is up.
Okay.
The reviewer, please ask questions.
So the first question to the opponent, do you think their data is convincing?
I think some of the data is convincing, but some of them are not. Just like the previous thing, I think the chart should be drawn left, not just the linear one.
Okay, so my reporter, can you turn to the steps?
Please.
Yes. She asked you the angle of the chopstick side. How is it? How do you make sure it is vertical when it sticks into the parts?
To make sure the rod is vertical, because you can see that we give the hole to the rod on the wooden stand, and we confirm that the hole to the rod is vertical to the vessel.
So on the top of your picture, is it pulled by like your hands?
Pull by hand.
Yes.
Yes, we pull the vessel by hand, and then we read the data on the force scale.
So how do you like make sure that your directions are set, like the way you pull it out?
You say we should make sure the pulling force should be vertical.
Yeah.
Oh, okay. Maybe next time we can use another experiment setup instead of use the hand pulling.
Okay.
Okay, the reviewer, more questions. Okay, you have 2 minutes to prepare your review. Okay, the review, please take the floor. You have 4 minutes.
So the topic today is right here, and the report's main focus is the relevant parameters and the significant shifts of the granular material. And they explain why the vessel would be lifted. So discussion 1 is opponent asks is the state unstable? Like can it affect the result? And the reporter said it affects just a little. And discussion 2 is the opponent asks, does the picture the empty spot of the picture affect the results? And the reporter said it will affect. So discussion 3 is why did they shape the vessel? And the reporter says they want to control the same pack. Discussion 4 is the opponent said, do you agree that the speed and angle will affect the result? And the reporter said yes, but didn't do the experience on the angle. Discussion 5 is the opponent asked, the main thing that you are discussing is the maximum value. And the reporter said you can use the maximum to prove the phenomenon. And discussion 3 is the opponent said what kind of material is the vessel. And the reporter said it's 3D printed. And discussion 6 is that the opponent said, do you think the material of the vessel matters the friction? And the reporter said, yes, it matters. So I asked the opponent, do they think that their data is convincing? And they said some of them is convincing, but the chart has to be fixed. And I asked how the reporter controlled the angle of the chopstick, and he said he had a thing that controls it. And I asked him about the thing he pulled by hands, and he said that maybe next time he won't pull it by hand. Yes, thank you.
Okay, the concluding remark of the report in 2 minutes.
I'm going to talk about a concluding remark. And the first is theoretical. The opponent suggests us we should have taken kinetic friction into the consideration, and we should put the kinetic friction formula. And about the experimental, we could try to find out different way to better control the packing friction, to minimize our error bar, and to control the attached area of granular material. And we made a mistake when I'm talking about my diagram, that this is not the exponential, it is a diagram about the cubics of x. So about the experimental, the reviewer suggests us that we can change our method of pulling the vessel. I think this is a really good idea that we can make our experimental data more accurate, and we could try to investigate more parameters such as the material of the vessel and the angle of the rod that stick into the vessel. Thank you.
Okay, the question time.
asking about quantum zone. It's regarding its depth and the force, right? So obviously you don't agree it's linear.
Yeah.
So if not linear, what do you think it should be and why?
I think it should be the chart I drew on the board because
It's not linear, but what is that?
I think it is like related to each other, but maybe it's not linear, but it's still related. So I think maybe drawing linear point isn't that accurate.
Okay. Thank you.
Regarding to that, I would like to ask you, the reporter, you said that is a linear fit. Then you got the linear fitting, the gradient coefficient is some number. So what is the physical meaning of that gradient, the fitting number?
Could you pardon what?
Yeah, for example, this one, your linear fit, the coefficient is 8 equal to 3.28. So what is the physical meaning of this one?
The physical meaning of this question, that is by these data about 3.28, that about the cell rate of this linear line.
Okay, excuse me, can you go back to your setup? Okay, here you said you for the whole experiment you use the same rod or use different rod? Same stick or the different rod?
We use the
Same one.
Yeah.
And here it said the diameter actually is 2.65 centimeters, right?
Yes.
And okay, can you go back, go to the page about the vessel, the size of the vessel, or the diameter of the vessel, the graph. Can you go back, go to that page.
Okay.
This is the diameter of the vessel, right?
Yes.
And you see the x-axis, right? It's around 1.5 centimeters to 3 centimeters, right?
So your rod is bigger in your vessel.
We have a data mistake in this diagram.
So could I answer for you? So we think that we made a mistake on typing. So this might not be the 2.65 cm. It should be millimeter, I think, because compared to the scale of my hand,
2.65 millimeters. That's very tiny, you know.
Yeah, maybe.
I would be surprised you get the third decimal place. 0.0265.
Just looking at the picture, 2.65 centimeter is reasonable. I think you make a mistake on the size of the vessel.
All right, thank you.
That's it.
Any more questions? No, this is call time. Okay, 66666.
No error. 66666.
Okay, for the opponent. 68766.
8766.
For the review. 55655.
55655.
there any comments in the review? Let's take a 15-minute break.
Question number 5.
Problem number 5.
Set.
A set. Okay. And 5 minutes preparation time. call the freestyle flow. You have 12 minutes.
Dear undergoing audience, opponents, and viewers, we are going to talk about whistling mash. My name is Li Qingdun, and my team is We're Family, and we're from Kaohsiung Municipal Kaohsiung Girls Senior High School. So, the problem statement. When a stream of water hits a rigid metal mesh within the range of the angles, a whistling tone may be heard. Investigate how the properties of the mesh, stream, and angle affect the characteristics of the sound of beat. This is our outline. First, I will talk about introduction, and then the theory and analysis, and then experiment and discussion, and last but not least is the conclusion. So for theory, a whistle is an instrument which produces sound from a stream of gas, most commonly air. And the theory behind the whistling mash experiment is based on the principle of acoustic resonance. When air is blown through the mash, it creates a vortex, or small eddies, in the airstream. And water by itself hardly makes any sound at all. So it is only when air is trapped by water in the form of bubbles that sound are heard. And the next one is when the water flows through the mash, it causes the sound of whistle. After going through the mash, the sound is reinforced by the cavity, forming a louder whistling sound. So this is my device and setup. We use a sound analyzer to measure the data, and so we can collect the data simultaneously after the sound produced. And this is the graph. This sound analyzer will produce. And so here is my experiment setup. We use a mesh and a pipe, and the water flows from the pipe and hits on the middle of the mesh. And to maintain the velocity of flow, I also use a pump to maintain the stream. So for device, I use mesh 1 and mesh 2. For the properties, in both mesh 1 and mesh 2, their diameters of cavity and mesh and walls are all the same. The only difference is the diameters of both, which is 0.02 cm for mesh 1 and 0.03 cm for mesh 2. So for experiment 1, we discussed how different degree affect the frequency of mesh 1. So for a control variable is the mesh 1, and the velocity and size of stream, and the distance between water outlet and mesh, which is 2 centimeters. And the independent variable is the different degrees. So as you can see in the peak, you can see that the smaller degree, the higher frequency and bigger intensities the mesh produce. The next thing I want to discuss is how different degrees affect frequency of mesh 1, which is the same as the previous page, but we changed the distance between water outlet and mesh. And also our independent variable is still different degrees. So as you can see in the peak, we can also find the result of the smaller degrees, the higher frequency and bigger intensity the mesh produced, which recapitulate the result from the previous page. For experiment 2, I discussed how different degree affect the frequency of mesh 2. So for control variable, we use mesh 2, and also the velocity of size of the stream. And the independent variable is different degree. And so to change the mesh, I look at this peak and also have the same result of previous pages, which is the smaller degree and the higher frequency and bigger intensity the mesh produced. So after comparing the result of previous pages, I create this chart, discussing how the velocity of stream affect the frequency of the mesh. So this, because the pipe only contains one velocity, so in order to change the speed, we adopt the distance between water outlet and the mesh. which is 24 centimeters and 2 centimeters. The upper charts are the mesh one and the distance between 24 centimeters, and the lower charts are the 2 centimeters charts. So we can see that the higher the velocity of string, the higher frequency and bigger intensities the mesh produces. And then I also want to discuss how the properties of each mesh will affect the result of the frequency and intensity of the sound. So for information, mesh 1 has a smaller host, which is 0.02 centimeters for each host. And mesh 2 has a bigger host, which is 0.03 centimeters. So also, comparing the peaks of each point, we also see that the smaller host, the higher frequency and bigger intensity the mesh produces. For conclusion, in both frequency and intensity, how the degree affects the frequency and intensity, we found out that smaller degrees will produce a higher frequency and intensities of both in this situation. And for velocity of water, we found out that higher velocity of water will result higher frequency and intensity comparing to lower velocities. And if we compare the holes of the mesh, we found out that the smaller holes of mesh will produce a higher frequency and intensities of the whistling mesh sound comparing to the bigger one. For discussion, after comparing all the results, I assume that the mixing of liquid and gas leading to instability, which is made even greater by the size and the capacity of the cavity, and the relevant parameters. The first one is the force of the water flow, and the second one is the diameters of the hole, and the third one is the angle of the mesh, and the least one is the length and volume of the cavity. So during the previous pages, I think that the water flow through the mesh can cause the sound of whistling, but to make the sound louder, I think it's because of the cavity, which is the mass here. The wall of the cavity will enforce the sound of the whistling sound. So to prevent the sound differ, we use the same walls of mesh 1 and mesh 2. So, and thank you.
Okay, the opponent please ask questions in 2 minutes.
Which is the highest decibel?
Which is the highest decibel? Yeah, okay. So, you mean by comparing which kind of vectors? Like velocity?
Yeah, velocity.
So the velocity of the string, which is here, you can see that we compare 24 centimeters and 2 centimeters. So here, the point is obviously higher in both frequency and intensity of the sound. And so if you're asking about the degree, I found out the smaller degrees will cause the higher intensity because when deploying in the smaller degrees, the mesh of the vertical axis will be smaller, so which is related to my experiment later.
And like, how do you actually like get rid of your background?
because it is hard to get rid of the background sound, but because of the frequency, we can't simply subtract it. So for example, if the difference of the decibel is 10, that means the difference between the sound is 10 times higher. So we first measure the background noise, and then we measure the noise, the whistling match sound.
Okay, the time is up. The opponent please prepare you in 3 minutes. And our opponent, please take the floor. You have at most 4 minutes for your speech.
My name is Mia Lin, and my team is called ABI. And for the problem statement, it's like when a stream of water hits the grid metal, which within a range of angles, a whistle's tone may be heard, and investigates how the properties of the mesh and stream and angles affects the characteristics of the sound and produced. And for this setup, got like a sound analyzer and mesh 1, which is 0.02 centimeters, and a mesh 2, and a pipe and a pump. And for their theory, their air trapped by the water forms bubbles and makes sound. And for analysis, different degrees affects the frequency. And also the velocity of the stream affects the frequency too. And for their conclusion, they said that the higher of the velocity of the stream, the higher frequency and the bigger intensity of the mesh products. And for their pros, it's
We got a lot of explanations of them, and the first on the water flow relevant. In your comments, it's like they maybe can get more formulas. So I think maybe you can just like start asking me questions.
Okay, discussion.
Like as you said that basically they got like a sound when the water went through like the match, right? Like because of the bubbles, like the resonant account hence it produced because when the water hits it, it will form yeah, like a bubble. Okay, and like can you just imagine like okay when today if you're putting like liquids in, like when you put like water or like other liquids, it will still make sound, right? But like what is like you put like sparkling water in it? Like sparkling water. Yeah. So like for like sparkling water, they have already had like bubbles in there. Like what is like still make a sound? The bubble isn't just conclude isn't the ingredients in the water. It is actually when the water hits the mash and it blow up and which can form the bubbles, not the yes. And what's y'all's like angle for the water? Like what's y'all's like angle for the water flow? Oh, how did I? So. And like, how did y'all like keep your flow like steady? Okay, so here is the mesh, right? And we cut the angle is here. So we actually use the vertical line comparing to the ground, so the angle can be calculated. And we use the protractor to measure the angle. And you talk about how did I maintain the state of flow. Okay, so we use the PVC pipe, which can make the stream more stable, and also we make sure it hits in the middle of the mesh, so that it won't hit other parts of the surface and affect our results. And then how do you like control the angle of like the mesh? Control the angle of the mesh. Oh, I use a protractor to adopt the angle. And then what's like the hitting spot? Oh, it's in the middle of the mesh. So we actually draw a dark point here to make sure it hits in the middle of the mesh. Oh, so you guys like to keep it in the middle like every time? Yes. Then how was like you know the formula? Well, we didn't have formula because this is actually just a phenomenon between the sound caused by water and mesh. So we do have the theory, which is it is caused by acoustic resonance. And do you think like the amount of the water like matters to the like do you think the amount of water like flow matters? Like amount of water flow matters to the sound? The amount of the water flow? Yeah. Like matters to the sound. You mean or is the water main? Yeah, I mean like when you like try to like dip the water down, it's like skinnier. So like what if you put like the bigger area of like water? Well, if we put a bigger area, then the point it hits on the mesh will be unstable. So we decided to use a certain distance, so the water flow will maintain. Okay. Then like will the height of the water balloon like matters? Yes, because we actually use this for experiment 3, which is testing the velocity, because from different height between the mesh and the water outlet, it will affect the velocity of the water and further affects the force the water makes.
And how do you track your figures?
You can see using sound analyzer. Well, first of all, we measure the background noise, and then we measure the background noise. We measure the sound of the whistling mesh, and then after calculations, for example, we put the decibels into the intensities and subtract the whistling mesh sound and subtract the background noise sound and make the charge into decibel again. So we can observe the phenomenon more clearly without other factors.
And do you think the sound will change, if you change the material of your mesh?
Well, if I change the material of the mesh, yes, it will. So actually, we despite mesh 1 and mesh 2, we also do other kinds of mesh, for example, plastic mesh and mesh that are softer. However, other materials cannot make the whistling sound. I think it is maybe because it has to be a metal, and then the softer mesh will make the water flow into the flow through the mesh instead of making bubbles.
You mentioned you guys get rid of the background noise. Then how do you measure your background noise?
We just
app or something?
It's like we divide it. We use the sound analyzer and then measure the background noise first, and then measure the whistling sound. So we actually calculate by ourselves.
Then can you just go over? I think there's a chart I forgot what's on the page, but it's just go up. Yeah, right. Can you describe why is there actually a down, up and down? Why are they 63? Why is it here?
So actually, because although we subtract the background noise, there is other the sound maybe be the water flow. This is the water flow. So there are other factors. However, after doing the calculation and consider other variables with calculation rings, we decided to set our aims on just comparing the peaks of each side. Because actually, the sound of the whistling mesh is very loud, and when you move the water to the mesh, there is a obvious high peak on this one. So we think that this is what the whistling mesh brings.
Also that will it still have a sound when the mesh is too small? Where's the sound?
You mean the size,
Yeah.
the diameters of the mesh?
Right.
I think it doesn't really matter as long as you had a point staple hit on the mesh. It wouldn't cost by the diameters because there's only one point causing the mesh sound.
And do you think they have a limit of it? A limit of the smash? That will have no sound?
Yes, because we actually do another mesh at a size that we couldn't measure the single holes of the size. and it cannot produce a sound because it is when the size is too small, the holes are too small, the mesh becomes softer.
You can make hole small, will the sound like what is that sound? You hole small.
Oh, I think it's like maybe it's tell like 0.00 something because the one I calculated, the one I consider is 0.02 and 0.03.
And you said that the bubble is a water his mesh to make. And what about like the natural proof?
The natural, because you mean caused by the water flow or this?
Different through water flow.
Oh well, it is included in the background noise because we first use the water flow and to measure the background noise.
Also, y'all also get rid of the frequency of the.
We try to.
I think that's probably it.
Okay. The reviewer, these questions in 3 minutes. Oh, sorry. Summarize of the opponent about the discussion.
Like as I just asked the reporter that he thinks that will the mash like is too small, will it still have like sound? And she said yes, because they also put like another experience about it. And I also asked her like it also had like a limit to it, and she said yes too. And also I asked her like if she changed the material of like the mash, will it actually like cause like the difference, like different sounds? And she said yes too, because like they also try another experience, which is like plastic and stuff, and the sound frequency is different.
Okay. The reviewer, please take questions in 3 minutes.
So from this reviewer from the States. So here is the first question for the reporter. So for this page, what is the relationship between the angle and the frequency here?
Oh, so in 15 degrees, a peak in both frequency and
In 2000 and for the 30 degrees is in 2000.
what?
Like so you investigate about the frequency,
Right.
and so what is the peak frequency here for
You
the
mean
90 degrees?
90 degrees.
What is the peak frequency here?
It is not really obvious, but we think that it is around 4,000.
Okay, so how do you think like do you think that they should investigate about more frequencies or only peak frequencies?
I think they should probably like investigate more about it.
Like okay, so please turn to the page that will the theoretical. Like also what is the origin of the sound? Like you mentioned. Like is it the air vibrated because of the water flow?
Yeah.
Yes. What is the origin of the sound?
The origin of the sound.
Like which part of the air vibrates because of the flow?
Like the air surrounded by the
The
water.
sound like inside of the mesh or under the surface of the mesh or what else?
I think both, but under the mesh there is a wall and can make the sound bigger. So I think the main sound is enforced by the under the mesh.
Okay, so what do you think?
I think mine is probably the same as hers too.
Okay. So you've mentioned that you remove other sounds.
Right.
Like how can you be sure that the sound is not caused by the flow? Like,
Oh,
yeah.
so when we compare the mesh and the flow, there is obvious high peak after significant changes. But we are not sure the other point is caused by the water flow or just the mesh. So we only compare the peak point.
So you don't think that when the water collision with the mesh, the sound shouldn't be counted?
Okay, time is up. The reviewer has 2 minutes to prepare. Okay, the reviewer has 4 minutes to review.
So, honorable juries and fellow commentators, I'm the reviewer Jason Lee from the Physics Institute High School. And I'm going to review problem number 5, without mention. So here's the summary of the report. First, for the reporter, they think that it is related to acoustic resonance, and when the flow of the water hits the middle part of the mesh, it will cause a sound, and the hollow part under the mesh will make the sound bigger. And for the theoretical analysis, they think that the water goes through the hose and make a sound, but they didn't provide a theoretical formula, just like what the woman said previously. And for the experimental confirmation, I think what they've done is like when the degrees become smaller, the frequency of it will become bigger. And for the diameter of the hose become smaller, the frequency will become bigger. And for the velocity of the stream become higher, the frequency will become higher too. So here's some pros and cons for the reporter. They've got a good delivery, and also they've got adequate parameters and comparison between each experiment. But also there are some cons for first, they didn't get an exact formula of the frequency, which our reviewers think that it might be possible to do. And also there are lack of the theoretical models to show the origin of the sound. And also their theory can't support the relationship between the parameters because they didn't provide why some of the parameters will affect the result in their theory. So here's the summary of the position. First, the opponent talked about the effect of background noise, and then the reporter said that they record a sound which contains only the background noise, and also that and for the opponent's performance, they pointed out some of the critical problems, like they have a lack of the formula, and also there's on the graph, it has shown random peaks on the graph, so maybe, and the reporter said that it's because the background noise. And also they didn't ask them to provide more about the theory, like how it will affect the characteristics of the sound. And here's the discussion part. The opponent asked about how to avoid the background noise, and the reporter thinks that they should record a sound of the noise and subtract it from the original noise. And our reviewer thinks that they could record the sound and use professional software like Audacity to further analyze the sound, like getting more peaks of them. And also, the opponent asked about will the material of the mesh affect the sound, and the reporters say that they think yes, but some of them can produce the sound, like the metal was best, and they've tried plastics too. And for our reviewer's view, we think that the material of the mesh will affect the vibrating frequency because the structure is different from each other. So here's the discussion. So here's another question from the opponent, like if there's any other sound make like the water hits the mesh only, and for the reporter they think that it's still it should be contained in the background noise. And here's here's some points for the reporter, like they missed the theoretical formula for their theoretical model, and this is my review.
Okay. Concluding remarks of the reporter in 2 minutes.
So, first thing I want to talk about is how to control the stability of water. We just use a manufactured motor and make sure the water hits the middle of the mesh and use PVC pipe to control flow. And it is actually really hard to conclude this phenomenon to formula, because since the sound of the flow is really, although it's smaller than the whistling mesh sound, it can still affect our result. So we will further investigate how to do this kind of formula in the future. And the next thing I want to talk about is the model of the cause of the whistling mesh is based on the principles of acoustic resonance, just like I was previously saying. When air is blown through the mesh, it creates a series of vortices, small eddies in the airstream, which can cause the whistling mesh sound. And so this is my theoretical model. And the reviewer said that I didn't compare how different parameters affect the whistling mesh sound. I did compare I compared 3 points. The first one is degree, and the second one is the velocity of water, and the third one is the hull of the mesh. And these are how it affects the frequency and the intensity of the sound. And I think that's all. Thank you.
Thank you for your review.
There's a question for the review and the formula. So what kind of formula you are looking for? You pointed out there's a lack of formula.
First,
Yes.
because of the water flow will be directed onto the mesh, and for the mesh, there should be velocity. And what I'm looking for is the formula for the value of the velocity and for the diameters of the holes. And when we put this into a formula, we'll get the peak frequency or other frequencies.
What kind of formula?
I can actually do this experiment, but I think my thoughts sound like this. About number of holes.
Can I ask
Yes.
For presenter, is there an error bar in your experimental data?
Yes.
Oh, so they are as small as that dot? Or?
I actually just calculate the average, but because it will be really hard to see.
You mean the error bar is that small?
Yes. Because the sound is really, the intensity of the sound is really big. So
how long did you average to get the data?
2 or 3 minutes.
So that intensity, the integrated or it's
actually it moves. Despite the peak, other points actually move slightly. However, the peak remains still. So I assume that is how what the whistling mesh sound of the frequency.
Thank you.
Is there any